Hello everyone, and welcome to our part 2 video on weird systems of equations. So what I have here is I have a systems of equation that I've written out for you, and we're just going to solve it. And we're going to solve it the old-fashioned way, which is we are going to eliminate some of the variables. So I'm going to work on eliminating my x's. I have an 8x on top, so I really like to have a negative 8x on the bottom. And so in order to do that, I'm going to take the whole thing and I'm going to multiply by negative 4. So then that gives me 8x plus 12y equals 20. That's just the first equation. I'm just recopying it. I'm not making any changes to it. And then this second equation, I'm going to multiply the whole thing by negative 4. So we'll get negative 8x plus negative 4 times 3y gives us negative 12y equals negative 4 times positive 5 is a negative 20. So now when I go to add things together, my x's cancel out, so I get 0. My y's cancel out, so I get 0. And the other side of my equation cancels out, so I get 0. So I have on this side of the equation 0, and I have on this side of the equation 0, which really is kind of confusing because we were supposed to be able to get a value for x or y, and now everything just went away, so we have the value for nothing. So that's why we call this weird. So what I want to do is I want to show you what this looks like on a graph. So here's our first equation, which remember was 8x plus 12y equals 20. And let's just make an xy chart for that graph. And then over here, I'll do the 2x plus 3y equals 5. And we're going to make an xy chart for that line as well. All right, let's start with this one because these are smaller numbers, so they're easier to do. All right, so I'm going to say, well, if x equals 0, then this entire term cancels out, right? Because that would be 2 times 0, which is 0. So then we have 3y equals 5. So 0 plus 3y equals 5. And I'm going to divide by 3. Divide by 3, so y equals 5/3. And I could change that into a mixed number, which would be 1 2/3, but I'm just going to leave it like that for right now. Okay, so that is one of our points, and we need 2 points, remember, in order to draw a line. So let's pick some other number. Well, because this is all funky, I'm going to make my y 0 and then see what my x turns out to be. So now I'll just draw a line here. So that's 2x plus 3 times 0 equals 5, which would be 2x, this all goes away, equals 5. Divide by 2, I get x equals 5/2. So I'm just going to put that down here. Now again, I could change that into a mixed number, which would be 2.5, but for our purposes right now, I'm just going to leave it that way. Okay, so what I'm going to do over here is I'm going to do the same thing. I'm going to start with my x equals 0. So I get 12y equals 20 because this term goes away because I multiplied it by 0. So I divide both sides by 12. I get y equals 20/12, which is an ugly fraction that can certainly be reduced. I will divide it by 4. So 20 divided by 4 is 5. 12 divided by 4 is 3. And I get 5/3. You should start to see some similarities here. Do you see that? How that first point is true under both equations? We're starting to see some weirdness coming along, aren't we? All right, well, let's do the other way. Let's make our y 0 and see what we get. So here we have 8x plus 12 times 0 equals 20. Again, this term is going to cancel out because 12 times 0 is 0. So that gives us 8x equals 20. Divide both sides by 8. x equals 20 over 8, which can again be reduced again by 4, coincidentally. 20 divided by 4 is 5, and 8 divided by 4 is 2, so that gives us 5 halves over there. And again, you will see that that is the exact same point we calculated over here. Now, we didn't have to calculate the same points. We could have calculated different points. It doesn't matter. I just think this makes it a lot easier to see what's going on. But you would not have to do that. So if I make myself a little chart, I'm going to start plotting these points. So my first purple line is x equals 0, y equals 5/3, which we said was, remember, about 1 2/3, so that's about right here. And then our second line is x equals 2.5 when y equals 0, so right here. This is our line. This is also our line for this one, because we have the exact same points. So what we are learning here is that this system of equation resulted in two identical lines that just lie on top of each other. Now, the problem with the graphing method, as we have discussed, is that it is imprecise. So sometimes Fred will say, graph these two equations. You'll graph them. They will look like there is a point of intersection. But if you had drawn your graph perfectly, you would see that the lines lie on top of each other. For instance, you can imagine that if this is my first line that I've drawn, I could have drawn a second line that looks like this, and I would have a point of intersection right about here. I might think that there was a solution to this problem, but there's not really, because truly the lines are on top of each other. So you might ask yourself, how do I know if the lines are on top of each other? That seems like a great thing to know before I do all the work of graphing stuff, and I agree with you. So let's go back to our original equations. 8x plus 12y equals 20, and 2x plus 3y equals 5. Those are our two equations. And this time what we're going to do, instead of solving the system of equations, we're just going to put each line in slope-intercept form and see what that does for us. Okay? So let's take our first equation, which is the 8x plus 12y equals 20. And then once we're done with that, we'll do the 2x plus 3y equals 5 over here. That way you can just see it nicely. All right, so 8x plus 12y equals 20. We want to put it in slope-intercept form. That's our goal. So remember, that means that we want our y by itself. So y is over here, which is awesome. So we just need to get this x over on the other side. So remember, we flip the side, we flip the sign. So we're going to keep 12y on this side of the equation, but we're going to move this 8x to the other side. So that becomes negative 8x. We flipped the side that it was on, so we're also going to flip its sign. The 20 remains positive. Now, we have y by itself, which is, well, we have 12y. So we sort of have y by itself, but it's multiplied by 12, which is no good either. So we're going to divide by 12. And remember, we talked about how we have to kind of divide each of these variables by 12. Otherwise, you start kind of, it gets a little bit messy. So y equals negative 8 over 12x. That's just another way to write it. I just moved the x to the side. Plus 20 over 12. Are you with me? I hope so. All right, now what we're going to do is we're going to reduce these fractions because these are icky fractions. So y equals negative. I need a number that goes into both 8 and 12, which is 4. So negative 2 over 3, because 4 times 2 is 8, and 4 times 3 is 12. I just divided by 12, divided by 12. Divided by 4 and divided by 4. All right, now x plus, and now we're going to reduce 20 over 12. And the way we're going to do that, so this one I divided top and bottom by 4. And this one, I think I'm going to do the same thing. I wouldn't have to, but it just so happens that those are good factors for those numbers. So 20 divided by 4 is 5, and 12 divided by 4 is 3. So this is our version of this equation, but in slope-intercept form. Okay, so the y is by itself, and I've reduced everything nicely. Now let's go over here and do the same thing with our red equation. So again, our goal is to get the y by itself, so I need to move my x. Flip the sides, flip the signs. So that becomes negative 2x plus 5. Moved it to the other side, and so I changed its sign. Okay, now I have 3y, so I need to divide everything by 3. So that gives me y equals negative 2/3 x plus 5/3. That is the slope-intercept form for our second equation. Now, if you look at these two equations, you should see some similarities. In fact, you should see a lot of similarities. In fact, they are the same formula. And since they are the same formula, you know that they are the exact same line. So, simply by putting in slope-intercept form, I can tell that they are the same line without going through the graphing and then without questioning whether my graph is good enough to really determine if it's the same line. So, that's how you would go about solving that and understanding what's going on without actually graphing. Now remember, this first number here, the one before the x, the coefficient of the x, this is your m value, right? And that equals your slope. So if your slopes are the same, but your y-intercepts are different, then you know that you have parallel lines. So you would have parallel lines if m's are the same. M of the first equation equals m of the second equation, but your y-intercepts do not equal. So b sub 1 does not equal b sub 2. That gives you parallel lines. Identical lines, which is two lines right on top of each other, that's where the two slopes equal and the two y-intercepts equal. So perhaps that's a good way for you to think of it. Let's do one more example, just to see if you're catching on. All right, so I'm going to give you a different set of formulas. I'm going to give you 3x minus 3 equals 9y. That's your first formula. And then your second one is going to be x minus 3y equals 1. And what I'd like you to do is I'd like you to put both of these equations into proper slope-intercept form. And then let's see what we can tell about the lines. So if I start with my blue equation here, I want to get y by itself. Y is on the wrong side. It's over here on the right side of the equation. So my very first thing that I'm going to do is just rewrite this problem so that I have my 9y on this side and everything else on that side. I'm just flopping them. Sometimes people say, well, don't you have to change the sign if you're going to flop sides like that? And yes, you do. But I also just changed it back. So if you want to flop it and change the signs, then you can change the signs again by multiplying by -1, and this is what you get. Anyway, I just moved it. Okay, so now I have 9y equals 3x minus 3, and this makes me happier because this is starting to look like a slope situation here, right? I have my coefficient, I have my x, and I have what will become my y-intercept. All I need to do is get y completely by itself. So I will divide everything by 9. So I get y equals 3 over 9, or 1/3 x, plus -3 over 9, or -1/3. So that is my proper slope-intercept form for my blue equation. Now let's head over to my red equation. So I have negative 3y over here, and we've talked several different ways of making it so that it's not negative, and one way that we can do that is multiply the entire equation by negative 1. So let's do that. So now we have negative x plus 3y equals negative 1. So I multiplied negative 1 by every term. All right, now I'm going to flop my x over to the other side, flip the sign. So this becomes 3y equals positive x minus 1. Okay? Divide by 3, divide by 3, divide by 3. This you could think of as a negative 1. So that gives us y equals x over 3, otherwise known as 1/3 x, plus negative 1/3. Whoa ho ho, look at that. We have the exact same formula for both the blue equation and the red equation. That means that we have the same line. So if you decide to graph this, you would graph it knowing that the line is exactly the same. So even if your graph is a little bit off and it looks like you have two different lines, you will know that you do not. So that is the end of our Weird Systems of Equation Part 2 that deals with identical lines.